Okay, welcome back for part two. We're going to talk about household wiring. And so we have a household wiring system. I'm going to draw it with a battery on it for a DC circuit, but the same applies to AC circuits. So in case you don't know, the difference between DC and AC. DC stands for direct current. And in a direct current system, you have a steady positive voltage on the positive end of the battery and a steady neutral or negative voltage on the other end, and it just is consistent. It's what anything that has a battery in it operates on, is DC current, right? DC circuits. AC is alternating current. For an AC circuit, I would use this symbol. Alternating current varies. It oscillates between plus and minus constantly. The main advantage to using AC current is that it can be transmitted for long distances with less energy loss. So there's less waste. And it means your power plant can be miles away from the city. And you ship it over high voltage transmission lines and you don't lose as much energy. So it's more economical. DC systems have to be much more localized. So for example, I can use a DC system to power my household, but I don't want to power an entire neighborhood that way. If you want some interesting reading about scientists having dramatics, you can look at the battle between Thomas Edison, who was developing DC systems for cities, and Nikola Tesla, who was developing AC circuits, AC systems for cities. And it was really quite dramatic and involved things like electrocuting an elephant to prove safety. So, some summer reading for you. Back to our household wiring. We would typically in a household at somewhere near where the power enters your home, you will have a breaker box that has all the circuit breakers. Those are the little switches that you flip when something goes out. Those are a bunch of ground fault circuit interrupts. That if you pull too much current on one of them, the switch flips and breaks the circuit so that you don't start a fire. After the breaker box, the rest of the wiring in the house, in the walls, and to every plug and lamp and switch and things, is on a parallel system. And the reason for this is twofold. Number one is every appliance, lamp, toaster, heater, you name it, gets the same voltage. Which in US households is 110 or 120 volts. In England, it's 240 volts. And secondly is they are individually switchable. So I can take and put a switch on each of these circuits and turn the lamp off, but the TV doesn't turn off, or unplug the toaster and the rest of the things in the kitchen don't turn off, right? If I was in series, unplugging one thing in series turns everything off. The same effect as a fuse. Also, the parallel system allows me to, when I turn one lamp on, all the other lamps that are lit don't get dimmer. right? If it was in series, everybody has to share the voltage, right? You do part of your voltage drop across the first thing and part across the second thing and part across the third thing. Well, if you flip the switch on one of the things in the circuit, everybody else gets more voltage, and so lights get brighter, lights get dimmer as you put things on and turn things off. So parallel is how your house is wired, so that it doesn't matter that there's nothing plugged in over there. Everything else in the room still works. So, handy information at some point in your life. All right. Good. So the last topic in the chapter is RC circuits. And I'm not talking about radio controlled, right? We're not talking about drones and cars. We're talking about resistor and capacitor circuits. So at the very basic level, we're talking about a circuit with a switch and a resistor and a capacitor. Okay. Now, with the switch open, nothing happens. With the switch closed, current flows through the resistor to fill up the capacitor. And so we get our maximum current at the beginning when the capacitor is empty. So that so I max equals I initial. Okay, so if you think about our capacitor in the filling a water balloon idea, right? When the water balloon is empty and I first turn the water on, it starts filling up really fast. But then as it gets fuller and fuller and fuller and more pressure builds up inside of the water balloon, it slows the flow of current down until some point it just stops. And that's what happens as we fill up a capacitor through a resistor. And we get our max charge in the capacitor at the end. When it is full. Okay, so our maximum current I calculate with V equals IR. Okay, because the only moment that you get that amount of current is at the very beginning, because there's nothing preventing the flow of current. And with charge, we use QVC, but we get our Q max when the capacitor is empty. Okay, obvious. Or I'm sorry, we get our Q max when the capacitor is completely full. There we go. All right, so we have a capacitor with C and a resistor with an R. Okay, so now how do we calculate things on the way there? So let me give myself a little room. I'm actually going to take this out of here too. Every RC circuit has what's called a time constant. And they use script T for that. And the times constant, measured in seconds, is equal to the resistance times the capacitance. So that's ohms times farads. Okay? And the time constant is the time to change by 63%. So if I'm charging up a capacitor, it's how long does it take to get it 63% full. If I'm letting the charge out of a capacitor, it's how long does it take to empty 63% out, right? So it's a change how much you got, whether it's current or charge. You're going to change it by 63% from where you are, okay? It works like half-lives with radioactive materials. Okay, and so if we look at how charge changes with time in a charging circuit, so starting with no charge and filling up, it fills up quickly at first, and then as it gets fuller and fuller and fuller, it eventually levels off, okay? And the place where it levels off is our Q max, that is equal to VC, okay? So we get up to that level where Q equals VC. One time constant is kind of just a little bit farther than halfway up, and that's tau. And that same amount of time later, where we get to 2 tau, we will be 63% of the rest of the way. And then at 3 tau, we'll be another 63% of the way, etc. Okay? So 63% of what you're doing every time you go through one time constant. The equation for that is that Q equals Q max times 1 minus E raised to the negative time over time constant. Okay, it's an exponential relationship. If we look at current over the same time frame, the current, when I starts out fast, and then it slows down as the capacitor gets more and more full. My I max comes from V equals IR, and I max equals V over R. And its equation is I max times, E to the minus T over tau. Okay? So for a charging circuit, that is how we calculate how full will it be after 73 seconds, or how much will the current, what will the current be 73 seconds after you start. Now, this version, the E to the minus T over tau, is the one that we use for discharging circuits for both Q and I. So this is charging, filling it up. You fill up the capacitor quickly at first, and then it gets slower and slower and slower as it gets stuffed, right? Once it's stuffed, then you're stopping your current, right? At the beginning, it flows in fast, and then it goes slower and slower and slower and slower till it stops. Okay. Now the discharging is the opposite. Okay. For discharging, which means letting the charges out of the capacitor, you start out with a lot of charge that squirts out really fast, because you're thinking about a really full water balloon. When it starts, it goes really fast, and then by the end, it's just dribbling. And that means that our Q equals Q max times E to the minus T over tau. And our current also is a depleting thing. We start out at Imax because when it first starts